Hey everyone. Today we're on Unit 6, Lesson 2. We're going to be talking about horizontal and slant asymptotes. Before we begin, let's kind of review some of the stuff we talked about yesterday with rational functions. And we're going to do a real quick review of x and y intercepts and how to find them when we're given a rational function. So if I give you a function, g of x equals x squared plus 3x minus 10 over x squared minus 4. And I ask you to just kind of write the function in factored form. We should be able to, by now, factor the numerator and denominator. So that would be factored form. And usually the reason we're writing it in factored form is so we can simplify it and write it in what we call simplest form. And if you remember from yesterday, there's times when we're going to use the factored form, and there's times when we're going to use this simplest form. If I'm looking at this function and I want to identify the restricted values of the function and the domain, well, I could say the restricted values, remember, they come from when the denominator is set equal to 0. So looking at that function in factored form, we can see our restricted values are -2 and 2. Therefore, our domain would be the set of real numbers excluding -2 and 2. And we did go on yesterday to talk about the existence of vertical asymptotes and holes. Okay, we're not going to focus on that today. We'll do more with that tomorrow. Today, just real briefly, I want to talk about how we can find the x-intercepts, right? The zeros or x-intercepts of a rational function and the y-intercepts of a rational function. So when we're looking for the zeros of any function, we want to remember we set the function equal to 0 and solve for x. Okay. So if we set this function equal to 0 and solve for x, we're going to kind of see right away that if I was going to set this function equal to 0, one of my solutions is not going to work in the function. So whenever we're dealing with a rational function, we want to use the simplest form when we're identifying x-intercepts. So we're going to take the simplest form and set that equal to 0. And hopefully you see that when you go to cross multiply, no matter what's on that denominator, that's going to go away. And our x-intercept is -5, or you could say the point -5, 0. Okay, so just on a little side note, you're just going to set the numerator equal to 0, make your life easy. What is the y-intercept of the graph of the function? So with the y-intercept, we plug in 0 for x. And when we're finding the y-intercept, it's easiest to use our original. So go back up into the original. And if you plug 0 in for x, you'll see almost right away that anything that has an x in it is going to cancel out. And you're just going to be left with the constant in the numerator and denominator. And if you kind of clean that guy up, you get 5/2. So our y-intercept is 5/2. Or you could say 0, 5/2. Either one is acceptable. All right, so we will be using that more tomorrow. I just kind of wanted to go over it today so it wasn't all brand new tomorrow. Now let's talk about what the real lesson today is about. Okay. Today we're going to be talking about how to identify those horizontal, or what we can call slant asymptotes in a rational function. So when we're dealing with rational functions, we can have three different possibilities. And before we even get started, let's talk about what a horizontal or a slant asymptote represents. Okay. When it occurs, it describes the end behavior of the graph as x goes to infinity or x goes to negative infinity. So if you recall from our polynomial unit, right, that's our end behavior. What happens as I plug in really big x's or really small x's? What's happening at the end of the graph, not what's happening in the graph. So basically, our three scenarios is we can get a horizontal asymptote of y equals 0, okay, where it would just be the x-axis. We can get a horizontal asymptote that's some number. So as x goes to infinity, x goes to negative infinity, our graph is going to settle at 0. As x goes to infinity, as x goes to negative infinity, our graph is going to settle at some number. Each of these are considered horizontal asymptotes. Okay. And that number would be the same from either side. Then we have this thing called a slant asymptote. And in a slant asymptote, that's going to wind up being some sort of equation of a line. Okay. And basically, as x goes to infinity, our graph can hug up here. So it would be like that. And as x goes to negative infinity, it could be like that, or from either side. That really doesn't matter. But this we call a slant asymptote. And based on what's going on in the original function, that's going to determine whether your x-intercept, I mean, your horizontal asymptote is 0, whether it's some number, or whether it's slanted. Okay. Might be important to note here, the graph of a function can intersect a horizontal or slant asymptote. And again, we'll see more of that tomorrow when we're doing the actual graphing. So we're just going to talk about the rules. How do we identify horizontal or slant asymptotes? And remember, we're going to be dealing with what we call end behavior. Okay, so in end behavior, if you think about it, we always talked about the term with the highest power, okay, with polynomials. That was how we determined it. So we're going to kind of do the same thing here. We're going to focus on the numerator and the denominator. So we're going to compare terms with the highest degree. So we'll let n equal the highest degree in the numerator and d equal the highest degree in the denominator. And I'm talking about the entire term. And basically the rules are just this. If n is less than d, you have a horizontal asymptote at y equals 0. This means that the denominator has a highest power. I call this bottom heavy. And what happens here is you're dividing by a bigger and bigger and bigger number. So eventually your graph is getting smaller and smaller and smaller and closer to 0. That's all. It's a very easy thing to understand. If n equals d, if the two denominators are the same, let's say x squared over x squared, those numbers, no matter how big they are or how small they are, they're just going to cancel out. And your horizontal asymptote is going to become a ratio of their coefficients. And the last case is when n is bigger than degree, or what I call top heavy. So if the top power is higher, we're going to have two cases, two things that can happen here. In case 1, n is 1 degree higher. In this case, we're going to have what we call a slant asymptote. So that comes in the form of y equals mx plus b. And we're going to use long division to help us find it. And in case 2, n is 2 or more degrees higher. And in this case, there's no horizontal asymptote or slant asymptote. Okay, nothing. And that we're not going to worry about. I'll give you one example just to show you how to identify it, but we're not going to deal with it in this course. So basically in this course, we're dealing with y equals 0, y equals a ratio, and case 1. Okay. So now we're going to look at actual functions with actual, real numbers in them and try to make some sense of this. And it will be extremely easy. If we look at the first example and we want to find the horizontal or oblique, should have mentioned this. Oblique is just a fancy way to say slant. Okay. And so we're going to do that for the following functions. R of x equals x minus 12 over x squared, 4x squared plus x plus 1. That's that polynomial in the numerator. That would be the highest power, the term with the highest power in the numerator. And from the polynomial in the denominator, I take out the term with the highest power. So I'm comparing x and 4x squared. Now I'm simply going to look at their powers. When there's no power there, it's x to the first. Which number is bigger, the top or the bottom? So the bottom is a bigger number. The denominator is bigger. I call it bottom heavy. There's no work involved. When it's bottom heavy, it's a horizontal asymptote and it's y equals 0. That's it. In example 2, term with the highest power, term with the highest power. Take them out and compare powers. Now I'm just looking at the powers themselves. So I have 8x squared over 4x squared. Think about it. No matter what number you plug in, since the powers are the same, these are going to cancel each other out. And you're going to be left with 8 over 4. So no matter how big the number gets, your answer is going to sort of settle at 2. So this is a horizontal asymptote. And the equation of that line is y equals 2. And we should always write horizontal asymptotes and vertical asymptotes as equations of lines. In example 3, I'm just going to give myself, I know this example takes a little bit of room. Okay, so I'm going to kind of identify my highest powers. Highest power, highest power. I'm going to look at them on the side to see what I'm dealing with. 4, 3. So I'm top heavy by 1 degree. So this is top heavy. By 1. So that's going to be case 1. N is 1 degree higher. So in order to find this slant asymptote, remember, this is going to wind up being a slant asymptote. I have to use long division. So I'm going to divide the numerator by the denominator. I can't use synthetic division for this one because I'm not dividing by x minus c. If you were dividing by like x minus 2, then you could. But because this is a more complicated polynomial, we have to use the long division. We reviewed this last week, so I'm going to go quick. X cubed goes into 3x to the 4th, so this is going to be 3x. Minus 3x cubed plus 3x. Now be careful when you're doing your subtracting line. Okay. So I was missing a couple terms. I didn't put in placeholders, so I'm just going to make sure I line things up correctly. So now x cubed goes into 3x cubed. I have to multiply by 3. Subtract. Negative x squared. So I'm going to have 2x squared minus 3x minus 3. X cubed goes into 2x squared. It doesn't. So last week we said that this would be like a remainder or something. We're just going to stop. We're going to ignore this. Okay. That does not matter. What we divided by, what the quotient up top, what's left, that's our slant asymptote. Okay. And that's how we would identify the slant asymptote. So somehow in this graph, if we were thinking about it, we'd have some sort of line like that, and our graph would be doing something close to that line. Again, we will focus on that more in the next couple of days. Today, it's just learning how to get them. And in our last example here, I identify my top power. I identify the term with the highest power in the denominator. When I look at these and analyze them alone outside, I see my top power is greater by 2, right? So this is top heavy, but more than 1. So this is going to be no horizontal or slant asymptote. So I don't have to do anything else. No work, no nothing. Okay, we're not going to study those this year. Okay, so you should have an idea just how to do the basic algebra for each of these. I just want to remind you, when you're doing horizontal and slant asymptote, you're not doing any factors. You're using the basic original function that you started with. We do have one more example I was going to work on today with you. I'm actually not going to work on it. If we were in the classroom, I would say work on this on your own and you could ask me questions. So that's what I'm going to do here. Okay, I'm just going to sort of identify all the things listed. X-intercepts, Y-intercepts, vertical and horizontal asymptotes. I know I'm going to have to factor this, so I might as well start. And it's also a good idea, 2x squared plus 7x plus 5. It's also a good idea, even if you're not asked to do it, to just kind of in your head know what the domain of this function is. So x can't equal -5/2 or -1. Okay, that's always a good kind of thing to kind of have in your head what numbers you can't plug into this function. X-intercepts, Y-intercepts. X-intercepts, I use my simplest form. And I set the numerator equal to 0. So my x-intercept is -5, 0. For y-intercepts, I can go back into the original, plug in 0 for x. And if you don't want to do all this writing, of course, you can eyeball it, because really, in the end, you're just going to get 5/5, which is 1. So my y-intercept is 1, or the 0.01. My vertical asymptotes. Vertical asymptotes, how do we get those again? Vertical asymptotes is the factor that does not cancel. So, right, it's the excluded value from the factor that doesn't cancel. We might as well talk about where the hole occurs here. My hole is going to be from the factor that does cancel. So I'm going to have a hole at when x equals -1. If I want to know the y value of that hole, I could just plug it back into the simplest form. And for my horizontal or slant asymptote, I'm not sure which one I have yet. Go back to the original, term with the highest power, term with the highest power. I'm going to put a 1 in front of this so I don't ignore it. The powers are the same. So my horizontal asymptote is y equals 1/2. What we're going to do tomorrow is we're going to put all this stuff together and make a picture out of it. Okay, see you then.